Hi, in this chapter I will talk about the differentiability or the derivative. Take for example these two graphs representing two functions. These two functions represent, let's say for example, how much two companies, a red company and a yellow company, are earning per year. So we can notice from these graphs that these two companies are making money and making more money each year because the graphs are increasing. But let me say, for example, if at 2019 the company in red earned a given amount and the company in yellow earned another amount, okay, and in 2020 or 2020 the company in yellow earned a given amount, in red another amount. Okay, so if I look to these graphs, what is the difference? Both companies are earning more money each year, but the difference is that the company in red is earning more money per year than the company in yellow. Of course, the amount reached in here by the company in red will be reached also by the company in yellow at some time in here, for example. Okay, but it will be in 2021. So the company in yellow will reach all the amounts reached by the red one, but it will be delayed. So it will be reached after a given time. That's why there's a difference between these two graphs. Both are increasing, yes, but the first one is increasing faster. And to know that it's increasing faster, we should look how much it is increasing with respect to the x-axis, so to the time. So in a given amount of time, how much the company in red increased and how much the company in yellow increased. And this ratio between the increase in y with respect to the increase in x is the ratio that will give us the rate of change. So how much fast the company is earning money, or how much fast the function is increasing. So let me take another example. If I take now these two graphs, the first one is making like this and the second one is making that. And if these two graphs represent as well the variation or how much a company is earning, let's say per year, and if in here it's the year 2019 and in here it's the year 2020, okay, we can notice that these two companies during 1 year they increased from a given amount to another amount, and they both reached the same amount by the end of 2020, and they both started with the same amount in 2019. So the ratio of the difference in the money earned, so in y, with respect to the difference in x is the same. So I will recall what I already explained. So I said first that the ratio y1 minus y0 over x1 minus x0, which is the difference between the y of the yellow and the y of the yellow, so this is y0, y1, with respect to x0 and x1. So this ratio will give me an idea about the rate of change, but this ratio is clearly not enough, because in this case the ratio between the yellow one and the red one is the same, even though these two functions are not they don't have the same behavior, because the function in red started very slow and then it increased fast. Let's say the first 6 months in the year were bad, they didn't make money, and then in the last 6 months they made a lot of money, while the function yellow, the yellow company, it was making money linearly according or through the year. Okay, but clearly the ratio is not enough. It gives an idea about how much the change was during a year, but it's not enough because it doesn't show what is happening during the year. And this is a big difference between these two companies. That's why this is not enough. What we should do is to take closer check-up points. So instead of measuring between 2 years, I will measure, let's say, during 1 month, each month, to compare. And also it's not enough because we don't know how the company is performing during 1 month. So we will take closer checkpoints. That's why we will go as much close as we can to x0. So let's say if we have a function increasing like this, and we would like to know at a given point how much the function is behaving, or how much the rate of change what value the rate of change is reaching. So I will take a point x0 and then another point x1, but I will be moving x1 closer to x0 as much as I can, and I will be measuring the rate of change y1 minus y0 over x1 minus x0. So moving x1 to x0 as much as we can mathematically will be the limit. That's why we'll be calculating the limit of this ratio, which will be written like this. It's the limit of f of x minus f of x0 over x minus x0 when x tends to x0. So I will be taking a point x0 and then a variable x that will be getting indefinitely close to x0 to calculate the limit of this ratio, which will be the rate of change, and to be called the rate of change at the point x0. Having this rate of change at each point will allow us to know the behavior of the function at each point, so we will no longer have the problem of two points and without knowing what is happening between the 2 points. So this ratio will be called f prime at x0, and it will be what we call the derivative of f at the point x0. So we define the derivative at a point x0 of a function f defined on I as being the limit when x tends to a. In here we have a instead of the x0 I used in the explanation. So it's the limit when x tends to a of f of x minus f of a over x minus a. So the function f is differentiable at a point a if and only if this ratio exists and is finite. It means that the function f is not differentiable at the point a when this ratio does not exist or is equal to infinity. And this limit will be denoted f prime at the point a and is called the derivative of f at the point a. Now we can write this ratio in another way by choosing h equal x minus a. So this is the a change of variable. So the point will be a, so we are calculating the derivative at a, and the point that is moving close to a will no longer be x, but it will be a plus h, because it's a plus a given step, which is h, and the limit will be calculated when h tends to 0, so when a plus h tends to a. So we say that the function is differentiable when this limit exists and is finite, and this ratio is called the rate of change of f between a and a plus h. Now, of course, when we talk about a limit, when h tends to 0, it means that h will be tending to 0 from the right and from the left. So we'll define the right hand derivative and the left hand derivative. The right hand derivative is the derivative when h tends to 0 plus, so from the right. When this exists and is finite, then this limit is called the f prime right of at a, and it's the right hand derivative of f at a, and also we have the left hand derivative. And we say that f is differentiable at a when the right limit exists and the left limit exists and they are equal. And when they are equal, the derivative of f at a will be equal to this value, which is the left limit and the right limit. This is a and r in here. Take for example the function absolute value of x. If you calculate the derivative at 0, it will be f of 0 plus h minus f of 0 over h. So f of 0 plus h, so this is the rate of change before going to the limit. So f of 0 plus h is the value, absolute value of h, minus 0 over h. So this is the ratio, the rate of change. Now if we go to the limit, when x tends, or when h tends to 0 plus, so h comes towards 0 with positive values, so the limit will be plus 1, the limit right. And if you go from the left, this is L left, the limit will be minus 1, because it will be minus h over h when h tends to 0 minus. So these two limits are not equal, these two values are distinct, so f is not differentiable at 0, because the limit exists, right, but it's not the same at the right and at the left. So f has a left-hand derivative, it has a right-hand derivative, but it doesn't have a derivative at 0. Also, if you take the function g of x equal x2, the ratio will be g of, if we calculate the derivative at 0, of course, the ratio will be g of 0 plus h minus g of 0 over h, which will be h2 over h, so it's h. And this tends to 0 when h tends to 0 plus, and it tends to 0 as well when h tends to 0 minus. So now the right limit and the left limit are the same of this ratio, so g is differentiable at 0, and its derivative is this value, which is equal to 0. Now of course, if you take a function and you take 2 points on this function and you calculate y1 minus y0 over x1 minus x0, this will be the slope of the straight line going through these 2 points. Okay, but when you calculate the limit of this ratio when x1 tends to x0, which is the derivative at a point x0, if this is x0, then you will be calculating the slope of the tangent at this point. So the slope of the tangent at the tangent's point, so the slope of the tangent of a function at the tangent's point is equal to the derivative of this function at this tangent's point. This is what we call the graphical interpretation of the derivative. Let us try now to write the definition of the derivative a bit differently. So if f is differentiable at a point a, then we know that the limit of f of a plus h minus f of a over h when h tends to 0 is equal to f prime of a. Okay, so when we say that the limit is equal to f prime of a, it means that if h tends to 0, when h becomes very close to 0, the function f of a plus h minus f of a over h will become very close to f prime of a. And very close, it doesn't mean that it's equal. We say that the limit is equal, it means that we are getting close to this value, but we will not be reaching maybe this value. So the function will be very close to f prime of a, but there will be always a difference between f of a plus h minus f of a over h and f prime of a. That's why we call epsilon of h this difference. So epsilon h is the difference between f of a plus h minus f of a over h minus f prime of a. And this difference, of course, will be a function that tends to 0 when h tends to 0. Because when h tends to 0, this ratio will become very close to f prime of a, and the difference will become very close to 0. So epsilon of h will get closer to 0 when h tends to 0. And consequently, we say that a function f is differentiable at a if f of a plus h equal f of a plus h f prime of a plus absolute value of h times epsilon of h. So using this equality in here, we were able to write what's in here by making first getting f prime of a on the side with epsilon h and then multiplying everybody by h and etc. We will obtain this equality in here. And this equality is useful in our context in here to prove that every function f is differentiable. If a function f is differentiable at a, then f is of course continuous at a. So any differentiable function is continuous. Why? Because if it's differentiable, then we have this, and having this, if we take h to 0, then this term will get close to 0, will go to 0. This one as well will go to 0. So f of a plus h will tend to f of a. And if f of a plus h tends to f of a when h tends to 0 from the right and from the left, and the value is equal f of a, the value of the limit, then this is the definition of the continuity at a point a. Then f is continuous at the point a. Now, using this equality, or this equality is even much more interesting. We'll be dealing with such expressions in the last chapter, but right now I will make a small interpretation of what's written in here. So this is the expression that we obtained in this paragraph for the differentiability. Let's try to read it a little bit differently. So I will rename a little bit the variables so it can be more readable. Let's consider that the a plus h will be x and the a will be x0. So we'll have f of x equals to f of x0 plus x minus x0 f prime at x0 plus x minus x0 epsilon of x minus x0. Okay, so if you look closely, what's in here is the equation of a straight line, and more particularly it's the equation of the tangent to the curve of the function f at the point x0, because the equation of a tangent can be written y equal f of x0 plus x minus x0 times the slope. But when it's a tangent, the slope will be equal to the derivative of the function at this point. So this is the equation of the tangent. So what's in here is the y, which is the equation of the tangent. And what's in here is f of x. It's the function. It's the image of a point x. So what we are saying in here, that the image of a given point x is equal to the value, or the image of x on the tangent plus a given value. I will try to illustrate this on a graph. So if you take a function and a tangent at a point x0, okay, so if you take another point x, the image of x, so the image of x is what's in here, right, is equal to the image of x on the tangent, so it's the value in here, plus a given value. So this is what represents the difference, and I will put it in red, the difference between these 2 points. You see? So we are saying that the function f can be approximated by the tangent, but we will always have a small difference. And this difference, it has an expression. It can be written like this. So it's something that goes to 0 as x tends to x0. So if x gets close to x0, this error will go to 0. And it's true, because at x0, this error is exactly 0, because the function intersects the tangent. And as I said, this is something that we will interpret more and explain more in the last chapter. I will talk about it later in details. We can prove now some properties of the differentiable functions at a point A. So if A belongs to I and lambda is a real number, f and g two functions differentiable at A, then the sum f plus g is differentiable at A, and the derivative of f plus g at the point A is equal to the derivative of f at A and the derivative of g at A. And this can be easily proven using the definition of the limit. So to prove that this is true, we need to prove that the function f plus g, if you apply the rate of change to it, we will obtain f prime of A plus g prime of A. So we will calculate the limit of the ratio f plus g of A plus h minus f plus g of A over h will be f prime a plus g prime a. So this ratio is equal to 1 over h times f of a plus h plus g of a plus h, and then it's minus f of a, so it's f of a in here, and then g of a, what's in here. So we'll have two expressions. The first one is the derivative of f at a, and the second one is the derivative of g at f at a when h tends to 0. In the second property, if we have lambda f differentiable at a, then the derivative of lambda f at a is equal to lambda times the derivative of f at a. And this can be proven a little bit as in the first, as for the first property. The third one, it says that a product of two functions, so the function product f times g, is differentiable at a as well, and the derivative of f g at a is equal to f prime at a times g a plus f of a times g prime at a. So let's take a look about the proof of this property. So if we take the ratio, the rate of change of fg, it will be fg of a plus h minus fg of a over h. And here we will add and subtract this value. So adding and subtracting this value will allow us to have from one side the derivative of f at a, and from another side the derivative of g at a. So we'll have f prime of a times g of a plus h plus f of a times g prime of a. And when h tends to 0, this will become g of a, and we will obtain the result. So in the fourth property, we'll prove as well that that 1 over g is differentiable at a, and the derivative of 1 over g will be minus g prime a over g squared a. And in the last property, we have the ratio f over g, which is differentiable at a, and its derivative at a is equal to f prime a g a minus f of a g prime a over g squared of a. And they can be proven in the same, in similar ways as in the other ones. We can also prove that if we have a function f defined at I and g defined at j, such that f of I is included in j, so now g round f will be defined, then if f is differentiable at a and g is differentiable at f of a, then g round f defined from I into R will be differentiable at a, and the derivative of g round f at a will be equal to g prime of f of a times f prime of a. Have you ever used this result anywhere? Of course, yes. If you calculate for example, the derivative of, I don't know, cosine x squared, you say that it's equal to what? You are used to say that it's equal, of course, if we calculate at a point A, it will be equal to 2a times minus sine a squared, right? So what we did in here is considering that this is the f of x, and g of x is equal to cosine x, so cosine x2 will be g of f of x, and the derivative will be the derivative of g, which is minus sine, at the point f of a, so it's at a squared, times the derivative of f at a, which is 2 times x at a, so it's 2a. So you already used this result without knowing that this is the correct formulation of the theorem. It's the derivative or the differentiability of the composite function g round f at a point a.